Bristol is quite fortunate in being awarded 2 AI hubs that will be centered here and another one with a significant presence here. I'm fortunate to be leading one of them. It's Informed AI, Information Theory for Distributed AI. So let me talk through that. Yeah. When we think about distributed AI, we tend to think, like our last speaker talked a lot about individual AI bots, which are capable of wonderful things. But actually, we're already in a world where there's large-scale distributed AI systems. When you're on the stock market, there's a bunch of smart agents running their own, like especially if you're doing fast quant trading, there are people running their own algorithms. We'll soon have smart traffic, a bunch of cars running around, running their own systems, things like that. So, and each of these systems has its own incentive structures, has its own algorithms. They're heterogeneous. They don't necessarily have the same design goals. So in general, like the sorts of behaviors that can emerge from here can be quite unpredictable, can be quite surprising. And the goal of our hub is to understand the fundamental limits of these sorts of systems, maybe get some organizing principles, and also tell us how to design them well, how to run algorithms on them. So the tool that we've chosen to use as a primary tool to understand this is the tool of information theory. Now, you may not have heard of the tool, but it was founded in the 50s by this person called Claude Shannon, and it really powers much of the data-centric world we live in. Like your cell phones are running a gazillion different algorithms that rely on this theory. The internet does, even things like DNA sequencing algorithms run on those things. Your data storage devices, anything that has some information processing happening in it is built on the foundations of the tools of information theory, which tells us fundamental limits of what an information processing task can do, and then algorithms that can come close to these performance limits. So as such, it's a good tool to use to understand the fundamental limits of large-scale systems where information is being shuttled back and forth, right? And in our hub, the 3 primary themes we'll be focusing on. Notice I'll be using the future tense. We just got funded in February. We're sort of getting off the ground. Much of this is aspirational. We have a lovely team coming together, but so what I'll be talking about are our goals and our current expertise, but we're looking to expand. So 3 themes that we'll be focusing on are, well, trustworthiness. So you have a large system with, as I said, different agents doing different things, computing things. Well, how much can you trust the output, right? Again, if there's someone feeding malicious data, how much can you actually trust the output of that? Heterogeneity. So again, when there are different AIs with different capabilities interacting, then how do you get them to work collectively? And I'll talk a little bit about some examples of this shortly. And then finally, connectivity and resilience. So again, when you have a large number of AIs, how they interact to each other also matters. Not everyone can talk to everyone all the time. There's a cost to communication. So the network structures, what if some communication links go down? Can you still do what you set out to do? If one car in your smart traffic grid cannot talk to the nearby car, well, how reliable is your traffic flow going to be, right? So questions like that. We are centered at the University of Bristol. Our academic partners are at Durham, Cambridge, and Imperial. We have an initial set of industry that we're working with. We're very happy to work with others, hint, hint. So please reach out to me. And one last slide on why this is a good thing to be doing. Well, the theory is for AI, but it's also for the practice of AI, how to build systems that are fundamentally close to the best you can hope to do. And we have in the UK a strong history of this expertise. It was founded by Claude Shannon in the US, but many of the people at the inception of the theory of information were giants in their field and were based out of the UK. All right, so in the remaining 5-ish minutes I have, let me talk a little bit about our current team, the academics co-leading this with me in other institutions. And I'll talk through some of their capabilities shortly. So these are some of the initial projects that we'll be taking on. So one team, which is very hands-on, works with robotic systems and actually implements some of these decentralized control systems, is working on coordinating these systems. So the thesis here is, well, as previous speakers have alluded to, one of the themes of the future is going to be robotic systems, large-scale robotic systems, and how they communicate and coordinate is of course going to be important. We've seen, for example, maybe news videos about the Amazon warehouses where, few human workers, lots of robots trundling around, and, drone swarms, things like that, right? So this is the coming future. But getting these things to work is tricky. As you have larger and larger fleets of these robots trying to do something collectively, simple things like making sure they don't bump into each other, but also do it efficiently, go around their tasks efficiently, form the right formations, coordinate with each other. The computation cost starts becoming prohibitive. Like how to actually design your systems to move well starts becoming a bottleneck. So how to integrate sensors so you have sensors distributed throughout your field of vision, how to integrate this into your design algorithms is a challenge, and AI helps with that. How to make formations that can move collectively through your space. AI works with this. These are all results from a test bed from one of our colleagues in Cambridge, Amanda Prorock, a leader in the field of distributed intelligence. Here, I can't show the video, I neglected to download it in time, but like existing algorithms, for example, you have a fleet of robots trying to move through some obstacles, and classical systems often run into issues like, each individual robot has its own sort of incentive to move, but then if they try to move together, well, there's not enough space for them to go together. And of course, what they should do is sort of, take turns, right? Me first, you next. But just breaking those deadlocks is surprisingly hard to do in a principled manner, and AI has been helping with things like that. All right, moving on to another theme. So I apologize, I'm going to be whizzing through all these lovely different things that different people in our team are doing, right? In the remaining 2 minutes, I'm going to talk a little bit about, for example, some work that we do. So CAT scans, trying to figure out what's going on inside a human brain. When I first heard of a CAT scan, this was my vision, right? Luckily, no cats are harmed in the scanning of brains. What's really happening is you pass some X-rays into your body, something comes out, and the relationship between the input and output tells us something about the system. The same is true for networks. We pass something into the network, something comes out somewhere else, and using this, we can infer the structure of the network itself, which tells us something about how resilient it is to errors, which could be adversarial or random, and that's one of the aspects that we'll be looking at. Another aspect, at some point I'll run out of time, I'll just stop, but another aspect is we have some collective data to merge, to do some computation on cloud computing. But how do we know we trust, say, Microsoft Azure or Amazon the Amazon Web Service or Google? So maybe we want to distribute the data so that everyone has a little piece, and collectively they're computing something, but no one person, no one system can corrupt the data irretrievably, can corrupt the computation irretrievably, can learn too much. So how do you do this in a principled manner, close to the fundamental limits? That's one aspect here. Okay, in the 30 seconds I have, there's quantum networking, and this is important, and we are designing algorithms for quantum networks, right? Distributing entangled bits and qubits is quite important. And then the last couple of slides, so differential privacy. This is a deep theory that figures out how to compute information on large data sets without leaking information about any specific individual. Like you want to do a population-wide survey about incidence of cancer or something, but you don't want to leak information about a particular person's medical history. So what is the fundamental limits of this, and how do you do this in large systems? Or how do you coordinate in a manner so that, like let's say you're trying to pull together a bunch of people to communicate over a wireless system, how do you coordinate so that you can still communicate efficiently? Okay, I'm out of time, I'm going to stop here. But I hope you get the sense that we have a really exciting team with some really cool people working on interesting problems. We're hiring postdocs. We're really happy to talk to industry. So please reach out. I'm easy to find. All right.